Okay, let's jump right into this explainer. Today, we're looking at how we build a true digital twin. Why? Well, to make absolutely sure our parts don't fail under load before we ever even touch a piece of raw material. As engineers, our ultimate goal is to design systems that work flawlessly in the real world. But getting there? Honestly, it can be pretty brutal. If we get the math wrong in the physical world, we're dealing with the massive cost of wasted materials, completely wrecked production schedules, and the terrifying pressure of catastrophic physical failure under load. So, to completely mitigate that risk, our entire process today has to start in the virtual world. To keep things perfectly systematic, we're going to follow this roadmap. First, the digital twin advantage. Then, inside Fusion 360, sketching and constraints, the power of parametric, and finally, we'll wrap up with the live recipe analogy. All right, section 1, the digital twin advantage. Let's look at exactly why we simulate before we build. Let's be real. The old way of doing things was just brutal. Manual techniques like milling and turning are incredibly time-consuming, and man, are they costly when mistakes happen. Back in the day, if your design criteria changed, it literally meant scrapping thousands of dollars of physical metal or plastic and starting completely from scratch. But by creating a digital twin first, we completely flip the paradigm. We can rigorously test for strict dimensional accuracy and mechanical strength prior to any manufacturing whatsoever. We take a virtual assembly, run it through intense physical simulations, and meticulously check for stress concentrations, friction points, and thermal behavior. And we do all of this before a single multi-million-dollar machine is ever turned on. It is an absolute game changer for cost and quality control. Moving on to section 2, inside Fusion 360. Let's talk about where we actually build these highly accurate digital models. So notice how the cloud acts as the central hub here. We absolutely do not want to reinvent the wheel by bouncing between clunky, disconnected programs. That's just begging for catastrophic file conversion errors, right? So instead, we use a cloud-based environment like Autodesk Fusion 360. This platform cleanly integrates CAD, which is your 3D design phase, CAM, which is the precise manufacturing data that actually generates the tool paths for your CNC machines and 3D printers, and CAE, which handles those heavy-duty engineering simulations. They all live perfectly, seamlessly in one place. And because it's cloud native, an entire global team of engineers can collaborate on a single part at the exact same time. It basically mirrors modern software development workflows, but for highly complex physical hardware. Okay, section 3, sketching and constraints, building the foundation. Let's get into the weeds of how we actually start building. Before we can test an assembly, we have to build it from the ground up. And when we design, we follow a very strict sequential process. First, we lay down the rough 2D shape. Next, we apply strict geometric rules. And finally, we completely define the model to lock it into place so there is absolutely zero ambiguity. Think of this as laying down the impenetrable mathematical foundation of your digital twin. If this foundation is loose or sloppy, the entire model is going to collapse the second you try to update or change it later. So the crucial point to remember here is that we never just eyeball a shape, ever. We apply constraints to force those lines to behave in various specific ways. If a line needs to be perfectly vertical, we mathematically constrain it to be vertical. We use perpendicular, parallel, and tangential rules so the sketch physically cannot break later down the line. In Fusion 360, these actually show up as little visual glyphs, like the perpendicular and parallel symbols you see right there. And listen, these aren't just polite suggestions, they are these strict laws of physics you are permanently imposing on your 2D drawing. But of course, here is the ultimate engineering dilemma. What do we do when the client suddenly decides the part needs to be twice as big? Or what if a mating component you ordered suddenly arrives with a completely different diameter? In traditional drafting, this was an absolute nightmare. It kept engineers up at night. Which brings us to section 4, the power of parametric. Let's look at how modern CAD completely solves this exact nightmare. Parametric modeling is a system where mathematical relationships dictate the entire geometry. It acts as an incredibly powerful risk mitigation tool. Instead of typing in a static, quote-unquote, dumb number like 10 millimeters for a hole and just praying it never needs to change, you create an intelligent variable. The entire 3D object is therefore generated by an underlying adaptable equation. Now, we can control this math using model parameters, which the software generates automatically as you dimension your sketch. But far more powerfully, we use user parameters that we manually dictate. Imagine having a slider for your dimensions. User parameters are incredibly useful if you have a known set of specific constraints for your features.
For instance, imagine you're designing a complex series of industrial pipes. The internal diameter might constantly change to adjust for pressure, but the physical material thickness, that must always remain exactly the same to prevent the whole thing from bursting.
And this right here is where the absolute magic happens. Let's say you define a user parameter named wall thickness, and you set it to exactly 2 millimeters. You can apply that single mathematical variable to 50 different interconnected components in your assembly. Now, what if the engineering team runs a really harsh stress test and realizes the part is buckling and needs to be stronger? You don't go back and manually edit 50 individual parts. No way. You simply change that one single wall thickness variable to 3 millimeters, and bam, that change instantly propagates across the entire assembly history in real time. It's perfectly recalculated in seconds. You can even use complex logic, like if-else statements, to ensure specific dimension physically never drops below a structural safety threshold.
Finally, Section 5, the live recipe analogy. Let's make this totally concrete.
If parametric modeling sounds like an abstract mathematical concept, let's break it down into something you'd find in your kitchen. It is literally like a live recipe. You simply tell the system you're cooking for 10 people instead of 2, and it mathematically scales up the ingredients, or in our case, your dimensions, so your part functions flawlessly. Because you applied those strict geometric constraints we talked about earlier, the software knows exactly how to stretch the flour, the sugar, and the butter without completely ruining the cake. The fundamental shape and relationships retain their pure design intent, no matter how much those primary variables flex and change.
What you should really take away from all this is that leveraging parameters and fully constrained sketches turns CAD from a simple drawing tool into a highly proactive failure prevention system. We are closing the gap between what we model and what we can actually manufacture in the physical world. By front-loading our effort into the digital twin, we save ourselves countless hours of wasted 3D printing builds, broken tools, and wildly expensive redesigns. I have seen exactly what happens when a static dimension is off by just a fraction of a millimeter. It results in a massive 5-axis CNC machine crashing a spinning spindle right into a solid block of titanium. It is terrifying and it is incredibly expensive. Parametric modeling ensures that that disaster never ever happens.
So I'm going to leave you with this to spark your curiosity. Now that you hold the power to build a flawless, infinitely adaptable digital twin, a system that bends and flexes precisely to your mathematical commands, what physical problem are you going to solve next?